All right, welcome to AP Chemistry. We're looking at Unit 1.5, looking at atomic radii of elements that are in the same group. And we were talking about, or we're comparing atoms in the same group. What we should be thinking about is a theme, and the theme should be number of energy levels and electron shielding. That should always be the theme. If nothing else is the theme, and so we're going to make that the theme of uh, what I talk about today. So we see I have skeletal Bohr models of magnesium and calcium, and I call them skeletal because they're not complete at all, not even remotely. But I do show the relative number, or show the protons in magnesium and the protons in calcium, and that's what those numbers are representing. 12 protons for magnesium, 20 protons for calcium. You can find that on your periodic table. All right, and so we're going to start off by looking at magnesium and calcium. And so the first thing we notice in magnesium, and we're going to go ahead and write the electron configuration, is that it has an electron configuration of 1s2, 2s2, 2p6, 2p6, and then also 3s2. All right, so it has three energy levels, and so we should see that. So we notice on my skeletal, I drew a nucleus, energy level 1, energy level 2. I need to draw another energy level, so I'm going to go over here to the circle and put a third energy level on this. All right, because we have two electrons. So this is kind of going through what we have. Let me go into fill shapes here, and let's go to circle and make this a little larger. Okay, so now maybe we'll be able to see our electrons. And so we're going to put in energy level 1, 2 electrons. 1, 2. In energy level 2, we're going to put 2 electrons. In energy level 2, this is 2p. The Bohr model does not take into account the s and p orbital, but it does take into account to the overall electrons in energy level 2, and there's 2 in energy in s, and there's 6 in p for a total of 8. So we have 2, it's going to be 4, 6, 8. All right, and then in energy level 3, we have 2 electrons, 1, 2. All right, and so we show that 2, 4, 10, 12 electrons are represented. All right, and so things to look at here. We want to look at the effective nuclear charge because we just want to, it's not the theme, but we want to look at it. And so let's take a look at the effective nuclear charge of this. So we notice that magnesium has 12 protons. And then we just talked about in that last video, hopefully you watched it, that we can differentiate between valence electrons and core electrons. And valence electrons are the electrons in the highest energy level or the outer shell. And core electrons are all other electrons. So if we look at it from an electron configuration standpoint, we would look at the highest energy level, that's the biggest number, it would be 3. And then there are 2 electrons there. And so we would say there are 2 valence electrons. All of these others that are not in that highest energy level, and unfortunately I can't do that, that are not in that highest energy level are core electrons. And how many core electrons do we have? 2, 4 plus 6 is 10. And we can count them in here. 2, 4, 6, 8, 10. And these are core electrons because they are not valence electrons. They are not electrons in the outer energy level. And so what we see there is we can get the effective nuclear charge real easily by simply looking at the number of protons. That's 12 minus, and then how many core electrons do we have? 10. So the effective nuclear charge of magnesium, not the ion, is 2 of the magnesium atom. All right, so we see that it's 2. All right, hopefully you can determine the number of core and valence electrons real easily, so you can do calculations like this, or if you just even asked a simple question like that. All right, so that's what we see there. And we're going to come back to this idea here in a second. But for calcium, we notice that calcium has a different electron configuration. So let's take a look at calcium. Calcium has 1s2, 2s2, 2p6. Notice this. Whoops, I didn't get that right. 2p6. 1s2. Oop, I got all of it wrong. 2s2. There we go. 2p6. There we go. 3s2. Whoa, does that look familiar? That's where magnesium is. Is that where we're going to stop on calcium? No, because calcium actually has 4 energy levels. So this is going to go all the way through 3p6 and then to 4s2. All right, so we should know something about valence electrons and elements in the same group. And what we notice is, we'll use a line here, these are our core electrons, right? These are all our core electrons. And then over here, let's go in orange. These are my valence electrons. And we notice calcium and magnesium are both in group 2, and they both have 2 valence electrons. You notice that? The difference is calcium has 2 valence electrons in the 4th energy level, whereas magnesium has 2 valence electrons in the 3rd energy level. So, but they both have 2 valence electrons, and they both react very similar for that reason. And so what we're going to need to do then is show the Bohr model with magnesium, or excuse me, with calcium having more energy levels. And so we're going to show this circle, and we're going to put this on here, and that's 1, 2, 3, and then 4. All right, and maybe I'll take that back real quick, and we'll make it look like the others. I think that's what I should have done. All right, let's make it look a little better. So 1, 2. All right, and unfortunately, I moved my electron configuration right in the way, so I'm going to have to move that. That moves everything, so let me do that real quick. Should have thought about that a little bit more. All right, so we're going to remove these lines. I think I already proved my point there. Well, I think. All right, so anyway, there's our valence. There is our core. All right, there we go. Now we're back to where we were. So we now know that we have 2 electrons in the first energy level. And so we'll go ahead and draw those in. 1, 2. We have 2 plus 6 in energy level 2. So we'll put those in. 2, 4, 6, 8. Then we'll put 2 plus 6 in energy level 3. 2, 4, 6, 8. And then we're going to have 2 valence electrons in the highest energy level. All right, so that's what we have. And then we can also calculate our effective nuclear charge for calcium. And calcium has 20 protons, but how many core electrons does it have? Does it still have 10 core electrons like magnesium? Well, let's count. 2, 4, 10, 12 plus 6 is 18. So it has actually 18 core electrons. And so its effective nuclear charge is 2. So when we look at Coulomb's law, we're looking at Coulomb's law, and I meant to put this picture in here, and I didn't do that. So let me do that real quick. I thought I did, but I did not clearly. So let's put that in there, and let's throw this in here. Control V, maybe not. Control V. There we go. We see Coulomb's law, and we were talking about this. The force of attraction is directly proportional to the nuclear charge. Well, we're going to say that magnesium and calcium, for all intents and purposes, with this equation that we're using, have the same effective nuclear charge. So it's not the number of protons, even though calcium has more protons. Its pull on its valence electrons is not quite as strong. Now, why is that? The reason that is because these valence electrons are further away from the nucleus than the valence electrons in magnesium. Now, why is that? Let's go to our theme. The number of energy levels. We notice that calcium has more energy levels. Therefore, its valence electrons are held further away from the attraction of the nucleus, making that force of attraction less. Now, that comes into play more so when we talk about ionization energy than it does atomic size. But nonetheless, I still want to bring it up even in atomic size, because the force of attraction is much less between these valence electrons and the nucleus because it has more energy levels. Now, why is calcium larger than magnesium, which is the largest? Obviously, calcium. Why? Because it has more energy levels. There you go. Now, the other factor would be electron shielding. So there's also a reduction in the force of attraction, because when we have two like charged particles, like an electron and electron, they repel each other. And repulsion is the opposite of attraction. And so we can see the valence electrons in magnesium and getting pulled towards the nucleus. There are some electrons that are in its way, and these electrons provide repulsion still while these are being attracted. The overall net force is attractive, but there's a little bit of something pushing them away so that the force is reduced. So there's still overall attraction, but that attraction is reduced due to the electron-electron repulsion between the valence electrons and the core electrons. Now we notice that in magnesium, it has fewer core electrons. Because it has fewer core electrons, there's less repulsion between valence electrons and the core electrons. But look at calcium. It has a whole bunch of core electrons, way more core electrons in the path of the in the path between the nucleus and the valence electrons. And so there's more electron-electron repulsion. We call this electron-electron repulsion electron shielding. And so these electrons, these valence electrons, are being shielded by the attraction of the nucleus by core electrons. And the more core electrons you have, the more electron shielding you have, and then the lower the force of attraction those valence electrons have for the nucleus. So because this has a lower force of attraction, not only because these electrons are held further from the nucleus, but also because of more electron shielding. And so that's the theme here. So how do we answer this question? And that's a great thing to go over right now. Let me get this where we can answer that. And let's go out of show your work. Obviously, you don't have a show your work here. This is just for the lecture portion, kind of go over the idea. And so what we see here is calcium is the largest species. So I asked which of these species has the largest atomic radius, and clearly I said calcium is the largest species. I probably could say calcium has the largest radius, but nonetheless, it's really easy for my grader to tell what my answer is. Now, one thing we noticed is that both calcium and magnesium are in the same group. What does that mean that they are in the same group? So if we go to our periodic table, and I'm going to put this over here, maybe here. Okay, there we go. We see calcium and magnesium are in the same group. They're both in group 2, right? They both have the same number of valence electrons. And they also have, what do we notice? They also have the same effective nuclear charge. It's very similar. Using that equation that we have, it's we get the same value. Now there's other more exact equations out there, but for all intents and purposes for this course, we can say that the effective nuclear charge is there's a negligible difference, and so we're going to say it's the same. All right, and so they have a very similar or the same effective nuclear charge. So calcium, though, has an additional energy level, and its valence electrons are further from the attraction of the nucleus. Additionally, the electrons in the additional shell experience more electron shielding than the valence electrons of magnesium. So both the additional energy level and an increased electron shielding result in a lower force of attraction between the valence electrons and the nucleus in calcium, making it larger than magnesium. So we see we're applying Coulomb's law. Coulomb's law talks about force of attraction, the relationship between distance and the force of attraction. And we see that in our equation, the relationship is that the force of attraction or repulsion, and in this case, we're talking about attraction because we're talking about negatively charged valence electrons to the positively charged nucleus. The force of attraction is inversely proportional to the square. So as the distance increases, the force of attraction decreases. If the distance is smaller, the force of attraction is larger. So they're inversely proportional in that way. All right. So hopefully I can get out of that. And so you can use an answer similar to this. You just need to put this in your own words. But for now, hopefully I helped you understand this concept, looking at elements in the same group. When we look at elements in the same group, or we're comparing atoms in the same group, whether it's looking at atomic size, ionization energy, and that type of thing, or any periodic trend that we talk about, the theme is always going to be energy levels and shielding. And then what should we know? If there's more energy levels, that means the electrons are going to be held further from the attraction of the nucleus. That means there's going to be a lower force of attraction. If there's fewer energy levels, that means electrons are held closer to the nucleus. That means the force of attraction is going to be greater. If we have more energy levels, we have more electron shielding. The electron repulsion that occurs from between the valence electrons and core electrons is greater, reducing the overall force of attraction they have for the nucleus, that valence electrons have for the nucleus. And if we have fewer energy levels, the electron shielding or the electron repulsion between valence electrons and the nucleus, the electron repulsion between valence electrons and core electrons is going to be much lower as well. So if we got fewer energy levels, less shielding. All right, and that means a higher force of attraction. All right, so hopefully all of that helped. Thank you for watching. Please like and subscribe.